So I'm going to show you a .NET Core console application that uses ML.NET to perform a machine learning task. I'll start with regression. So I'm doing supervised learning, I'm doing regression, which means that I have my data file and I have the answers in the data file. So I can train against those real answers. A regression means that my outputs, my predictions are numerical, it's a number. And what I'm going to predict is bike sharing demand in the Washington, D.C. area. So the Washington, D.C. area is, like this area of the US around Washington, D.C. And they have bike sharing stations on the street. So if you are a member, you can just undock a bike and use it and then put it in a different dock and leave it again. And it's a pay-per-use model. And it's pretty cool. Unfortunately, the company behind the bike sharing system needs to know on a day-by-day basis how many bikes will be in demand, because they have to put the bikes in the stations, and there's no point having hundreds and hundreds of bikes on the street if only 10 people use them. So a system that can predict at any given time how many bikes will be in use in Washington, D.C. is very useful. The bike sharing company can use that data to exactly supply how many bikes are needed. So what we're going to do, I have a data file. This is real data, by the way. This is actual data from a bike sharing company in Washington, D.C. I'm going to load it into a regression model. I'm going to train my model on that data. I'm going to evaluate the fully trained model to see how good the predictions are. And then I'm going to make a single prediction for a given time of day, a certain area in Washington, D.C. I'm just going to ask how many bikes are needed. So I'll show you the code. Let's see. So I'm in a PowerShell session. So it's just a console session. I'm going to quickly go to the correct folder. So I'm going to do a regression demo, and we're going to do bike demand prediction right here. And I will load Visual Studio.code and show you the code. Cool thing about Visual Studio.code, it's also multi-platform. It runs on Windows, it runs on Linux, and it runs on the Mac. It's an Electron application. So you can use .NET Core and you can use Visual Studio Code, and it will just run on any OS. I mean, it's useful for me because when I make these courses, I don't want people to have to install Windows, just to be able to attend the course. If you have a Mac or you have a Linux laptop, you should be able to just get started, So it's an important thing that I check when I create code for courses. All right, so this is the data file. You can see that I've got the date as the first column. And there is a season value. So the yellow column is the season. And then I've got the year, the month, and the hour split out into separate columns. The weekday number, I've got that one as well. And then there's some weather data. I've got the temperature, I've got the humidity, I've got the wind speed. And then all the way at the end, the final column is the number of bikes that were in demand at that given time. So the first row is the 1st of January, 2011. So, I mean, that's after New Year's Eve. So everybody has a hangover and is sleeping it off. So you can see that the bike demand is only 16 at midnight. So it's fairly low. So it's not 16 bikes. It's a normalized number. It's on so the scale has been compressed. So the number is 16. So actually it's not true. There's an actual number, 16 bikes. So New Year's Eve, only 16 people used the bike. And then if I scroll down, you can see the highest value is here, 110 bikes on, let's see, where's the number here? 1,500 hours, so 3 p.m. in the afternoon. So 110 bikes. So that was a holiday. Now, if I scroll down a bit, I'll take the 6th of January down here. And you can see that at midnight, let me scroll it here. So at midnight, demand is 11 bikes. But then when I move down, you can see at 8 o'clock in the morning, 8 a.m., 219 bikes. 219 bikes in demand. So it's a peak. And then at 1700 hours, so 5 p.m., 172 bikes in demand. And then 163 an hour later. So you can see there's a clear peak at around 8 o'clock in the morning when people use those bikes to go to work, and at 5 p.m., 6 p.m. in the afternoon when they go home again. So 2 peaks in demand. We can train on this data to make predictions for any date and time. So I'll show you the code. So here's the program. I'll go to the top. So to use ML.net, the only thing you have to do here's the project file. The only thing you have to do is pull in a NuGet package called Microsoft.ml. So you can see it's right there, version 1.1 I'm using. And you can see there's a second package called FastTree. That's a decision tree learning algorithm. It's not part of the standard package. I have to pull it in separately. If you don't use a decision tree, you can just leave that package out and only work with Microsoft.ml. So the only thing you need to do is pull in this NuGet package, Microsoft.ml, and then you're done. So here's the code. The first thing I need to do is create a class that holds a single record of data. So a single record of data is a date and time, the weather information, and the bike demand. So you can see I've got this class called demand observation, and that holds my, this single data record. And this final property right here called count is the bike demand, that corresponds to that date and time and weather situation. So that's always the first thing I do. You can see there's an attribute called load column in front of every property that tells the data loading algorithm from which CSV column to pull the data. So you can see that wind speed is in CSV column 13. So it's very useful. You can just load, with a single line of code, you can load a CSV file, and ML.net will then distribute the columns over the correct properties of your classes. So it's a nice way of importing data. I need a second class to hold a prediction. So it's right here, demand prediction. And this is the prediction that my model will make. So when I ask the model to predict bike demand, it will output this class. Then let's get started. So the first thing you need to do is load the data. So here's how you do it. A single method called load from text file. And you can see it's a generic method, and it uses the demand observation class. And that just pulls in the whole CSV data and just loads it. And what you get back is this data variable, which is an iDataView. It's a data view interface. And this is basically an interface on the whole data. Now this is lazy loading, so it doesn't load the data in memory. It just prepares a few things. Once you start training an algorithm, that's when the data gets pulled in record by record. So this works on huge files. You can take CSV files that are gigabytes in size, and you can use this code to load them and to train a model on them. So it's not a system where everything is copied into memory first and then trained in memory. So it's a nice model. A single line of code to load a CSV data. Then here's a very common thing we often do in machine learning. So Murat, that's one of the things, it's far better than Python. Yep. Well, in Python, I think you can import CSV files with a single line, can't you? I've not quite up to speed. I think I saw that in TensorFlow code. But I mean, nothing beats this level of compactness. So here's a lazy loading. Yeah, that's what you meant. Okay, so yeah, lazy loading. It's much better than Python. Yeah, this really goes on a record by record basis. Okay, so next step, what we often do is we split our data into a part for training and a part for testing. So the idea is we're going to train the model on the training part, and then when the model is fully trained, we'll ask it to make predictions for the test part. And then we'll compare those predictions with the actual answers in that test part. And the difference between those two, the difference between the predictions and the actual values, is a measure for how wrong the model is, or how right the model is. It's a metric that measures the accuracy of the predictions. And a very common partitioning is we train on 80% and we test on 20%. So that's what this line of code does. It takes this loaded data and it just chops it in two, and it reserves a part for training and it reserves a part for testing. Then, next thing is we build the pipeline. Everything in ML.net is pipelines. So a pipeline basically takes data, processes individual columns, and then trains a data science or machine learning algorithm on that data. And it's a sequence of steps. So here I start my pipeline, and I start with a component called concatenate. So concatenate takes all the columns that I'm interested in and all compresses them into a single column. So the first argument, it's called features, that's the name of the column that this component will produce. So it takes all these columns and it basically just takes all the data and joins it together, basically, just appends the data into one long data record and stuffs it into a new column. We have to do this because ML.NET can only train on a single column. That's a design decision that they made. So if you want to train on multiple columns, you always have to do this concatenate step first. You take the multiple columns, you basically squash them together into a single new column, and then you train on that single column. So there's always a concatenate step in the pipeline. So I've got my concatenate. Then I've got this thing, append cache checkpoints. That's just a little trick to actually load the data in memory to speed up training. This data file is fairly small, so I can just copy everything into memory and train on it really quickly. So append cache checkpoint is optional. You can leave it out, and then you can train on any size data file, or you can throw it in, and then training on small files will be really, really fast. Finally, I add my learning algorithm. So they're called trainers in ML.NET, and I'm using an algorithm called FastForest. Now, FastForest is an ensemble of decision trees. It's a specific data science algorithm. Sign up for my course. Sign up for my course, and I'll explain exactly what a decision tree is and the pros and cons of a decision tree, and how you can take these trees and group them into an ensemble, and then what the pros and cons of these ensembles are. There are all kinds of decisions for creating these compound algorithms. So FastForest is a famous data science algorithm, and it's basically a collection of decision trees that all work together in a certain manner. So if you join the course, I'll explain exactly how that thing works. So here I'm just going to use it. You can see I've added a bunch of parameters. I didn't have to do that because these parameters are the defaults. So basically the only thing you have to specify is the column to train on, which is features, and the column that contains the actual answers, which is label. So you can see this is supervised learning. The training algorithm wants to know where the answers are so that it can constantly compare its predictions to the answers. That's it. That's our whole pipeline. 3 components. So to train the model on the data, here's how you do it. Oops. A single line of code. We call the fit method on the pipeline, and that will train the model on the data that I provide. You can see what I provide is partitions.trainset. That's the 80% that I reserved earlier. So that's 80% of the data that I'm going to train on. And the output is this thing called a trained model. So you can see it's a complex class. It's a transformer chain. Basically, this is the trained machine learning model. It has trained on the data, its predictions are fairly close to the actual answers, and it's ready for use. Now, before I use it, I want to evaluate my model. How good is it, actually? So what I can do is I can ask the model to make predictions on the test set. Remember this 20% that I set aside for testing. So I call transform, which will use the model to create predictions on the test data, and it stores it into this predictions variable, which you can see, it's a data view. So this is a collection of predictions. And then my final step is this evaluate call. Evaluate will compare the predictions with the real answers, and it will return this class called metrics, regression metrics. And that thing is full of interesting variables that you can use to measure the accuracy of the predictions. So again, if you join the training, I'll explain what these things are. You can see there's down here, we have root mean squared error, or RMSE. We have mean squared error, and we have mean absolute error. So these are 3 scientific metrics that measure the accuracy of the predictions of a machine learning model. So these numbers will tell me how good the predictions are. Then the final step, I create a new observation So right here, here's my observation. So I've got this record, you know, of a certain time, a certain date, certain weather conditions, and I'm asking my fully trained model, how many bikes would I need corresponding with this data? And to do that, what you need to do is you need to create a prediction engine. So you take the model and you create a prediction engine. A prediction engine is just a class that allows you to run the model. So I'm creating my prediction engine and I'm storing it in the variable engine. And then you can see engine has this method called predict, and I can use that to make a single prediction. So I just call predict on my sample and it returns demand prediction. Remember, that's the class I defined at the top of the code that holds a single prediction. So it's that simple. I load my data, process my data, train an algorithm on the data, then I do a quick evaluation to see how accurate the predictions are, and then I create this prediction engine to run individual predictions on my fully trained model. And it's this flow every single time. No matter what you do in ML.NET, it's always this sequence of steps. And you'll see it when I show you the classification demo. It's the exact same sequence. So I'm going to run the code. So I'll go back to my PowerShell terminal. Here we go. So I'm just going to type .NET run, and it will run the console application. There we go. So you can do this on the command line. This is just PowerShell. I've installed the .NET SDK, and then I got this .NET command, and I can use it to run apps on the console. So here you go. It's loading the data, training the model, and making a prediction. So my the MAE, the third metric, MAE, mean absolute error. MAE, what it signifies is the average error in an individual prediction expressed as the number of bikes. So you can see my MAE is 75, which means that for every single prediction that my trained model makes, it'll be off on average by 75 bikes. So it's fairly high, actually. This is still a useful app because the bike sharing company could take a prediction. So you can see my individual predictions at the bottom. For the sample that I gave, the model predicts 331 bikes. So to be on the safe side, I can just add 75. So I could take 410 bikes, for example, and that will be more than enough to cover the demand. But 75 is a large margin. So if I were to use this commercially, I would have to optimize the code a bit further, maybe use a different learning algorithm, not use FastTree, but something else, to make more accurate predictions.